Shall we continue? Okay, so before the break, we looked at if I want to do least square, like what is the best possible function like that I could get, right? Like f star, which is basically the conditional mean of y given x. And we also discussed how we can never actually compute it unless you have access to p of x comma y. And we talked about how k-nearest neighbor and linear regression are trying to approximate this function, right? Right. So however, like we kind of missed one of the core issues in finding this function, which is the fact that we are looking for a function that has minimum expected prediction error in unseen data, right? But all we do in machine learning is to train the model with the training set, right? Like we want to minimize expected prediction error for any possible x, right? However, when you train your algorithm, you're trying to minimize the training error. So this is a big mismatch, okay? So we care about generalization error, but we are minimizing training error. What does this mean? This means that even if the ideal f star exists in my model assumption, like let's say I make an assumption for the algorithm, and the true f star also follows the same assumption, okay? Even if that is true, I might not be able to find this f star because I'm not minimizing the expected prediction error. I'm minimizing something else, right? So this is an important distinction that you should realize when you train your models, okay? Which is what we're going to talk about in this part. Like, so we're going to talk about the idea of empirical risk minimization. Okay. Again, we're going to do this in the context of regression. So I have some x, which is r power p, and I have some y, which is r, right? So for the previous session, like, so we did not make an assumption on f, right? So now we are going to make an assumption on what is f, okay? So my function f, okay, is parameterized by w, okay? Let's say I use f of x given w to be just simply w transpose x, right? So the moment I make this assumption that my model is w transpose x, right, I'm already eliminating functions which are not linear, right? So imagine that this is the class of all possible functions that exist in the world. Okay, linear function, quadratic function, like higher order degree functions, like any nonlinear function that you can think of, right? So this is the class of all the functions that exist in the world. The moment I make this assumption that my function is W transpose X, I'm saying, oh, I'm going to search over this really small set of functions, which looks like W transpose X. So then the learning boils down to just finding a W that is good, right? So every possible W gives you a function. Like you randomly sample a W, you're going to get a function. You're going to get one linear function, right? You sample another W, you're going to get another linear function. So how many such linear functions exist? Yeah? Yes. There are infinite number of linear functions that exist. So this is not, I say that this is a restricted class, but this is not that restricted. Okay, there are already infinite number of functions to search over. Okay. However, there is a larger infinity here. The moment you go away from linear model to nonlinear model, the space is even more infinite. Okay. So this W transpose X is not such a small space. Okay. So like there are infinite number of possible realizations of W transpose X. Okay. So this set of all possible realizations of W transpose X, right? Like we're going to call this the set of hypotheses that we are searching over. Okay, the set of hypotheses is basically a set which has W transpose X for every possible W. Is that clear? Now, a single hypothesis, H, okay, H is basically a single hypothesis, which is basically an instantiation of f of x given W for a particular W. You pick a W, you will get a H. Okay? So now I can talk about what is the expected prediction error if I pick a H. Okay, if I pick a H, then the expected prediction error is given by the loss of y comma h of x. So whatever the prediction of the hypothesis, that is h of x, you compare that with the true y, whatever loss function you use, right? Like, so this is basically integral L of y comma h of x, p of x comma y, dx dy, right? So we're going to call this expected prediction error as risk R of h. Okay. Now, the best possible H star that you could get is basically arg min R of h. H belongs to the hypothesis class. Okay. So this is what we are implicitly doing when we make a model assumption. Once I make a model assumption, I'm going to get a restricted hypothesis class. In this example, it is all possible linear models, right? Out of all possible linear models, I'm going to search for a H which reduces the expected prediction error. Is that clear? This is the first approximation in machine learning. Like, so whenever you do machine learning, you're making this first approximation that, okay, I'm going to pick a model. And I'm going to find the best possible hypothesis conditioned on the fact that I picked this model class. Is that clear? Now, the second big approximation that we are doing is because I don't have access to this joint distribution or to infinite data that exists in P of x comma y, I'm going to minimize this function only for n examples I got from the training set. Okay, so this is called the empirical risk. Okay, the empirical risk is given by R emp of h, which is basically 1 over n summation I is equal to 1 to n L of yi h of xi. Okay, so instead of minimizing this loss for every possible x comma y, I'm going to minimize this only for the given n examples. Is that clear? This is what I meant by empirical risk minimization. Okay, so what we do in machine learning is empirical risk minimization, which is basically find some h dash or h hat which minimizes the empirical risk. Okay, so h hat is given by R min of h belonging to h or m of h. Okay, on the other hand, h star is given by arg min, h belongs to h, h. Is that clear? Okay. So what I want you to understand now is typically we are in the process of finding this F star, right? Now, first, when you make the model assumption, when you make an assumption that this is the kind of models I'm going to learn from, you're restricting yourself already. Like you're restricting yourself to find H star, okay? The best possible hypothesis that minimizes the expected prediction error, okay? Now, in reality, this H star might not be equal to F star, okay? So already there's an approximation there, right? Now, the second approximation is because I cannot compute R of H, I'm going to compute R empirical H, which is the empirical risk on just the training data. And that is going to give me only H hat. Is it clear? So there is no guarantee that there's no guarantee for F star to be equal to H star or even H star to be equal to H hat. Is that clear? So if I have to draw this as a picture, right? So let's assume that this H is basically the set of all possible hypotheses. Every function in the world and their instantiations, okay? And H hat is basically the set of all possible hypotheses for a given model. Is that clear? Now, this figure that you see here, this is the big H. So it's basically all possible hypotheses that exist in the world, right? Now, the F star is somewhere here. Okay, the F star that we are searching for is somewhere here. Because this is every possible function that exists in the world, right? Like, so my F star should be somewhere here, right? Now, the first assumption that we are making, which is to picking a model, right? Like, so once you pick a model, there is no guarantee that F star is going to be within the H dash, okay? So for example, my H dash could be something like this. So then we were lucky. So we picked the best model class, which encompasses F star, right? However, it might also be the case that I picked a model class and the model class is somewhere here, which means even if I give you infinite amount of data, you will never reach F star. Is that clear? So this is why picking the right model is important. Like, so if you pick a wrong model, I can give you infinite amount of data. You can do whatever you want to do, right? Like, so you will never reach F star. Okay. Now, the second level of approximation is you are doing empirical risk minimization, right? Which means, let's say this is the best possible H star. There is no guarantee that you will reach H star because you're minimizing empirical risk, and you might only reach H hat, which is different from H star. Is that clear? Any questions? So these are the two most important approximations that we do in any machine learning setting, okay? So the first assumption, for the first approximation is we are approximating F star with some model. The second approximation is we are approximating the true risk with empirical risk. Is that clear? Yeah. F star is the function that we are looking for. So the function that generated the data. H star is the best possible function that you could get on the given model class. Okay. Is that clear? Okay. This looks like a very strong limitation, right? Like so it looks like we're making these two major assumptions. If any of this break, we cannot learn anything meaningful, right? Like, but we are going to talk about this assumption in detail, like, and figure out like whether we can still learn something useful. Well, of course, we can still learn something useful. That's why machine learning is successful, right? Like so it's important that you understand the assumptions. Okay, so we will talk about the implications of this like soon. Okay, so now we are going to look at the bias and variance of machine learning algorithms. Okay, so something that I touched upon towards the end of the last week, right? So we're going to look at bias variance decomposition. Let's take the last function, okay, which I'm going to use L2 loss for the discussion. So it's h of x minus y the whole square, okay? And h star is given by arg min h belonging to h, expected value of L of, sorry, L of y given h of x, okay? And we already know that h star is E of y given x, right? So this is what we derived in the previous session, right? Okay, so now I'm going to take this loss and I'm going to understand different sources that contribute to this loss or error. Okay, so let's take the loss function. So h of x minus y the whole square, right? So I'm going to do a small addition and subtraction here. I'm going to write this as h of x minus e of y given, sorry, e of y given x plus e of y given x minus y the whole square. Okay, so this doesn't really change anything, right? Like I'm just adding and subtracting e of y given x, okay? So now I can consider this as a plus b the whole square, okay? So this becomes h of x minus e of y given x the whole square plus e of y given x minus y the whole square plus 2 times h of x minus e of y given x times e of y given x minus y. Okay, so all I have done is just a square plus b square plus 2ab. Okay, now I'm going to take an expectation here. So expected value of the loss function is given by expected value of the first term, expected value of the second term, expected value of the third term. Okay, this looks like a very big derivation, but it is simple algebra. So expected value of h of x minus e of y given x the whole square plus expected value of e of y given x minus y the whole square plus 2 times expected value of h of x minus e of y given x, right, times e of y given x minus y. Okay, so we haven't done anything fancy yet. So I'm going to take this and simplify this in the next line. Okay, we're going to simplify each of these terms. Let's just call this as term 1, 2, and 3. Okay, so first I'll show you that The third term is just 0. Okay, so let's just get rid of it. So the third term is given by expected value of this whole thing, right? Like this is basically expectation over x, expectation over y given x. I'm going to multiply things internally. So it becomes h of x times e of y given x minus h of x times y minus e of y given x the whole square plus y times e of y given x. Okay, so I just multiplied the terms a minus b and c minus d. Okay, so now you can bring in the first expectation. So this becomes expected value of, when I bring in the first expectation, so h of x, e of y given x is not affected because it is not a function of y. Okay, it's a constant, minus h of x times, when I take expectation of y, this becomes e of y given x, minus this term is a constant, it's just mean square. Okay, plus the last term becomes e of y given x the whole square. So as you can see here, I can cancel this and I can also cancel this. So this whole thing becomes expected value of 0, which is 0. Yeah. Oh, we are doing expectation. The expectation is over x and y, right? So I'm just factoring it as x and y given x. So it's expectation over the joint distribution. Okay. So the third term is 0. So we don't need to worry about the third term. So let's just take the first two terms. Okay. Okay. So let's just take the first two terms. I'm going to do the first term, okay, so which is expected value of h of x minus e of y given x, the whole square, okay. This is given as integral over x, integral over y given x, h of x minus e of y given x, the whole square, p of y given x dy, p of x, sorry, dx. Okay. Now, can someone tell me what is this expectation? What is this expectation? This is basic probability. So think about it. So what is this expectation value? Yes, but you can simplify this. So I'm doing integral y given x, something multiplied by p of y given x d of y. Yes, it is a definition of conditional expectation. But then, is this term a function of y? Is this term a function of y? But this is not a function of y, right? H of x minus the mean square is not a function of y. So I can actually take it out. So I can write this as h of x minus e of y given x the whole square integral y given x p of y given x dy p of x dx. Now what is the value of this integral? 1, right? It's just the whole integral. So this is 1. So this becomes integral over x h of x minus e of y given x the whole square p of x dx. Okay, so this is my first term. Okay, let's keep this first term. So now let's go to the second term. The second term is given by expected value of e of y given x minus y the whole square, right? This I can write as integral over x, integral y given x, y minus e of y given x the whole square, p of y given x dy, p of x dx. Now, what is this integral? Again, this is another standard integral definition. So what is this integral? E minus mean the whole square, integral E minus mean the whole square P of x dx, or P of y dA, whatever. This is the definition of you guys did a probability review class, right? Yeah. Yeah, this is just the definition of variance, okay? So this is basically variance of y given x, P of x dx. Is that clear? Okay, so now I can write the expected value of L of y comma h of x as expected value of h of x minus y the whole square, which is basically the expected value of h of x minus e of y given x the whole square plus expected value of the variance of y given x. Okay? Now, if you did not follow the derivation until now, that's okay. You can go back and try to do it by yourself or watch the recording, okay? But for the purpose of this discussion, what is important is I can take the loss function and I can decompose this loss function into two parts. Okay, you can, if you want to forget about all the derivation, you can do that. Like, okay, so if you just directly trust me, like the loss function can be decomposed into two parts. Okay, so what are these parts? Let's just try to directly analyze these parts. Okay, we don't need to worry about how we arrived here. Let's try to analyze these two parts. Okay, first let's start with the second part. The second part is the expected variance of y given x. Okay, so do you see the model anywhere here? So we don't see h at all, right? So this is actually independent of h. So this is the most important part, okay? So the loss function can be decomposed into two parts, where the second part is the variance of y given x according to the true distribution, okay? In some sense, you can pick whatever model that you want, linear model, nonlinear model, nearest neighbor. You can do whatever you want. You will never be able to minimize the second part. Why? Because the second part comes from the nature. So this comes from the fact that the problem is stochastic. I have a stochastic problem to begin with. Like, so I have a problem where there's a joint distribution over x comma y, and there is some uncertainty that comes with the probability of y given x. Okay, so we're going to call this part as the irreducible minimum value of loss function. Okay, the second part actually explains why we can never have zero error in any prediction problem. Okay, this is very natural. So you have a stochastic problem. Like the best example I can give is we can go back to the housing price prediction, right? So we saw from the data that even if two houses have same size, they could have different prices, right? That was just one feature. You could add 10 features if you want. You can add, like, oh, the other example I can give is like, you can go to realtor.ca, see for houses in the same street, okay? Same street, which means like, so they're equally close to everything that you can think of. They can both be 4 BHKs, like 4-bedroom apartment, like houses, right? Everything will look exactly the same, but there is still going to be some fluctuations in the prices. So that is the variance. Okay, but like you might find 4 houses next to each other in the street. One is $1 million, the other one is $1,050,000, and other is $1,020,000. The other might be 900,000. right? Like, because there are some hidden factors we never know, which causes the stochasticity. So there is some variance that is inherent in any problem, right? So you will never get zero error. Like, so you're always going to, the best that you could do, even if you have access to the true function. So the best that you could do is like the first term goes to zero, right? When your h of x is exactly e of y given x, which by the way is not going to happen, right? Like, so even if it happens, right, you still have some error. So this is a stronger statement because what I tell you now is even if you have access to the true distribution, you cannot get zero error in your prediction because of the variance. Is that clear? Any question? So that is the main message for the derivation. Okay, so we derived this thing to show that the loss is decomposed of two things, like one that is model specific. Okay, we are going to decompose the model specific part further again. Okay, so there is a model specific part, which is where the h comes in. Whatever model you picked, it's going to have some error, right? But then there is also model independent part, which is the irreducible error. Is that clear? Any questions? Okay. Now let's take the first part, right? Like the model specific part, which is basically h of x minus e of y given x, the whole square. Right? So we're going to consider this model specific part, and we're going to further try to understand what are the various sources of error that we could have once we pick a model. Okay, so for this we are going to start considering the data set as well, because there is also this empirical risk minimization that we are doing, right? So we are approximating the true risk with empirical risk. So I'm going to assume that I have some data set D, which has n data points. Okay, and this means whenever I say h of x, it is actually h of x given this data set. Okay, it's not any h of x. Like, what is the hypothesis? Given that I'm using this version of data set. For different version of data set, you're going to get different hypotheses. Okay, so this function that you see here is actually h of x given d minus e of y given x, the whole square. Okay, so now I want to compute this error, like the model specific error, with expectation over the data sets. So expectation over the data set, h of x given d minus e of y given x, the whole square. Okay, again I'm going to do the same split. Okay, I'm going to write this as expectation of h of x given d minus e of d h of x given d plus e of d h of x given d minus e of y given x, the whole square. I'm just adding and subtracting a term here, right? And we're going to treat this as a plus b, the whole square. Okay, so this can be written as expected value of h of x given d minus expected value of h of x given d, the whole square, plus expected value of h of x given d minus e of y given x, the whole square, plus there's a 2ab, the whole thing is equal to 0. Well, no, not 0, sorry. Plus 2ab, right? So you can do the same exercise as before. Like when you do this 2ab, you will find that 2ab is actually equal to 0. This 2ab is equal to 0. Okay, I'm going to leave it as an exercise. So you can try doing that. So there is just two terms. Okay, so I'm going to rearrange these terms. Okay. I'm going to put the first term, the second term first, which is basically expected value of h of x given d minus e of y given x, the whole square, plus expected value of h of x given d minus expected value of h of x given d, the whole square. Okay. Now, what is the second term? This is also a classical definition. So what is the second term? Like I'm doing expected value of h minus e of h the whole square. What's the second term? This is also variance. This is another way to define variance, right? So this I can write as bias square plus variance. Okay. I'm calling this first term bias because I picked a particular data set, I got some error. Right? Like because I picked a particular model on a data set, I got some error. So that is my bias. Okay. So this is the error because of the bias, and this is the error because of the variance, which is coming just from the data. Like I picked a particular data set, right? And that is going to have some error. So that is the second part. Is that clear? So if I have to go back to the original expected loss, right? Now I can decompose the original expected loss into three terms. Okay. There is bias square plus variance plus noise. Okay. I'm going to define these terms. So the bias square is given by integral expected value of h of x given d minus e of y given x whole square p of x dx. Variance is given by integral expected value of h of x given d minus expected value of h of x given d the whole square p of x dx, right? And the noise is given by integral e of y given x minus y the whole square p of x comma y dx dy. Okay. Now, okay, let's try to understand these three terms. First, let's start with noise. So the noise term is just the variance from the process itself, right? Like this is irreducible. Okay. So then we have two other things like bias square and variance, right? Now, the variance, this source of error comes because you picked a particular data set, right? So this is the performance of this particular data set in comparison with the average performance across all the data sets. Okay. So that is the variance. Now, the bias is the error between your model class and the true function that you care about. Is it clear? So now you can see that like how different sources of errors appear, right? Like so first, so the moment you pick a model, you are getting the bias square as your error. Then the moment you pick a data set, the second approximation, you're getting your variance error. Okay? This you get anyway. You cannot change the third error. So the best thing that you could do is to pick a model that has least bias and least variance, right? Like you are looking for a model that, well, the ideal model that you're looking for is something that has zero bias error and zero variance error. Is that clear? So variance is because of the data set. So yes, so this is because of the approximation that you're making with respect to the empirical loss. Okay, so now if I want to summarize everything that we did today in one picture, Okay. Listen carefully. Even if you did not follow the derivation, like this intuition is really important. Okay. So for any problem, we have this hypothesis class H, which has all possible hypotheses that exist. Okay. And our source for the problem is somewhere here. Is that clear? So this is the source that is creating the problem x, y parameters for us. Okay, so x and y comes from a particular source. Okay, now because of the inherent noise in the process, the best that you could do is just E of y given x. Okay, and this gap that you see here, this is the noise. Okay, now typically we make some assumptions for these algorithms, right? Let's say I make an assumption. The moment I make an assumption, I'm going to restrict myself to some h dash, right? Now, within this h star, like h dash, the best that I could do is basically, let's say somewhere here, which is basically the expected value of h of x given d. Averaged over all the data sets, this is the expected error. Okay. Now, this gap that you see here, right? This is, sorry, this is the bias. Okay. Now, in reality, we will not even reach the expected value of h of x given d because we don't have access to all possible data sets. We have access to only one data set, right? So now, depending on your data set, you're going to reach one of these points, right? Now, which point you're reaching, that depends on the variance. So depending on the variance, you're going to reach just a simple h of x given d. Is that clear? So this, by the way, this is not a very accurate picture. Okay, so this is just for understanding purposes. Okay, this is not a very accurate representation, but this tells the point. The point is there is a source that is creating the problem, and machine learning is all about approximating the source with a function, right? Now, because I make a model assumption, I'm already making this bias error. Then because I work with just one data set, I also have this variance error. Even if I try to reduce both of these errors, I will never get zero error simply because of the stochastic nature of the problem. Is that clear? Okay. So now let's talk about the bias and variance in detail. Okay. So the bias variance trade-off. So this is what I hinted towards the end of the last lecture. Okay. So when you have a very flexible model, okay, like a model that makes the least possible assumption, okay, what does that mean? This means that this model actually has low bias. Okay. However, because the model is too flexible, there is a very high chance of being like too sensitive to the data set that you're looking at, which means the model could have high variance. Okay. On the other hand, when you have two rigid models, the best example is linear regression, right? So it has a very high bias. Okay. But the variance is low. Okay. So in general, if I plot the complexity of the model, okay, and bias and variance, right? So typically the bias decreases. as the model becomes more and more complex. Okay, so we're going to see more and more complex models in this course. Okay, so as the complexity of the model increases, the bias decreases significantly. A more complex model can actually cover a larger class of hypotheses. Okay, now this also comes with the risk that your variance increases as the complexity of the model increases. Okay, like the other way to say this is, as the complexity of the model increases, you need more data to reduce the variance. There's chance for overfitting, so you need more data to reduce the variance. Is that clear? Now, there's a sweet spot, right? Like, so the sweet spot here is somewhere in between. Like, so if you plot the true risk, okay, I'm going to plot the true risk. The true risk is going to keep decreasing up to some point, and then it will start increasing. This is the true risk. As you can see, there is a sweet spot where you trade off a little bit of bias with variance. Is that clear? Okay, so here is a situation question. So let's say I have two algorithms. Let's call them A1 and A2. Okay, so they both have equal performance. So they both are 95% accurate. Okay, but A1 is more complex and A2 is less complex. Okay, I want you to pick one of these two algorithms. Like, which algorithm would you pick? They have same performance. Like, they're both. Let's just say this is it doesn't matter whether it's training or validation. Let's just say this is validation performance. Okay, so the validation performance for both A1 and A2 is 95%. A1 is more complex than A2. So which algorithm would you pick? Simplest one. Why? Is there any other answer? Like, so, yeah?
I would say A2.
Yeah. So that's the same answer. So does anyone think you will pick A1 over A2? So why would you pick A2?
Mindset is like the Occam's razor. If there's a simpler way to describe the process, and it's probably the right one.
Why? Why is simplicity preferred? Try to go back to the discussion on bias variance. Okay, so yeah.
Just complex. The bias is my first thought was that you're confused, so like less resources to choose. But
that's a side effect, right? Like, yes, less complex models are are more efficient to compute. Yeah, that's more like a side effect of being less complex, right? Like, so yeah.
I would say for A1, like since it's more complex, it's tend to original, or it would have low variance and high bias.
For more complex, the more complex model is going to have low bias and high variance. It's going to have low bias and high variance. Okay, well, I think in general the answer is correct, right? Like, so it's a better idea to pick A2 instead of A1, okay, which comes from this philosophy that you always seek the simplest explanation, which is sometimes called as Occam's razor. Okay. Even though Occam did this in, I don't know, 1500s or 1400s, like before machine learning and computers, right? So, but this is more of a philosophical argument that when there are two explanations for something, like one is simpler than the other, it's more like you should pick the simplest one, like probably because it's sufficient to explain things, right? But in terms of the bias and variance that we discussed today, right? So the simpler model is going to have less variance, right? So their performance is same, but one has less variance than the other. So you pick the one that has less variance. Is that clear? So in general, you should go for the simplest possible model for the problem that you care about. But as we discuss more complex models in the future, we will realize that it is not easy. Okay, so this looks quite unintuitive, but we will see after a few classes that it's actually valuable to go for more complex models. Why? We will talk about it later. Yeah.
So it's kind of also, I prefer to have low value versus high value.
I don't want to say that we prefer to have high bias. We prefer to have low variance. Okay. That doesn't always mean that we need high bias. Okay. It's okay. As much as the bias and variance looks like a trade-off, it is not a trade-off. Okay. So right now it looks like we can only get low bias or low variance, right? But in the future, we are going to develop models which has both low bias and low variance. Okay, it's not impossible. Okay, it's not possible right now with the models that we have seen in the class because we have seen very few models, right? Like, so as we see more and more complex models, we will realize that there are actually smarter ways to construct your model such that it is both low bias and low variance. Is that clear? Any question? Okay, so we'll stop here and take a 10-minute break.